what have we been talking about up till now? We've been basically going over integrals, and we've been thinking of integrals as allowing us to find areas, right? So one of the things is we started off with the definition of the definite integral, and we're like, oh, the definite integral is just the area under f of x above the x-axis between a and b, right? And then we learned a bunch of stuff like, oh, that definite integral is defined as a limit. We talked about like, oh, where does that limit come from? Well, if you want to estimate the area, you just set up a Riemann sum, right, which is just a bunch of rectangles that estimate the area. And then we realized like, oh shoot, if you just take the limit of that estimate as the number of rectangles goes to infinity, then that's what the area is. And then we talked about a bunch of ways to like calculate that without having to actually calculate the limit, right? So we learned about the fundamental theorem of calculus and stuff like that. Okay, so what we're going to talk about today to now is you can actually do more than just find areas. You can also talk about finding the volume of a three-dimensional shape. Right? So if you're dealing with a two-dimensional shape, you can find the area of that two-dimensional shape. Right? 2 dimensions means like you have a width and a height. Right? Height times width gives you area. If we're talking about volume, that involves height, depth, and width. Right? That's 3 things. Right? So that would give you volume. So when we're talking about volume, we're talking about three-dimensional shapes. So how can you use integrals to find volumes? That's what we're going to introduce. So let me go into writing mode. Okay, that's not what I wanted. There we go, volumes and slicing. Cool. Okay, so let's talk about this. Like, how can you find volume? So this is going to be like a lot of drawing, so bear with me. It's a little hard to do. So normally when we're doing our two-dimensional shapes, we have our Cartesian plane, which is our x and y axis. And I want to point out that this is the positive x's to the right, the negative x's to the left, and then for the y axis, for the y, it's positive is up and negative is down, right? Right, so we're just like talking about the positive x part of the axis, positive y part of the axis, and so on. Okay, the way we draw this, the way we're going to draw this one is going to be similar, but it's going to be slightly different. For our 3 dimensions, here is going to be our x-axis. And then here is going to be our y-axis. And then like popping out of the screen is the z-axis. And going into the screen is the z-axis. Okay, so the positive part of the x-axis is going to be here. The positive part of the y-axis is going to be here. And then the positive part of the z-axis is going to be here. For now. Eventually we'll change that. But the whole idea is that when I draw these shapes, it allows you to orient yourself. Okay, so the z-axis is going to be coming out of the screen and into the screen, basically. The y will still be up, and then the x will be like horizontal. The reason we're doing this is so that it sort of matches. The reason we're doing it like this right now is that it matches your intuition about x being horizontal movement and y being vertical movement, and then our new axis, pops out of the sheet of paper that x and y used to be on. Does it sort of make sense that you can imagine that there's this sheet of paper for the x, y plane here? And the z-axis is what comes out orthogonally or perpendicular from that sheet of paper that the xy plane used to be on the left. Okay? Okay, cool. So, hope we're good with that so far. So let's draw our first shape here. Let's do it in green. So let's say you have a line like this, And a line like that. Okay, so do you see how it's above the x-axis? Okay, and then how should we do this? This red one is going to deviate out from the x-axis. So it's going to look like this. It's going to look like that. So let me like draw in the shape here. What you have is like a pyramid with a diamond base. I'm sorry, I started to do like a really janky job of drawing it, but I'm gonna put in some shading so you can see the four faces. Does everyone see that face right there? A question, Vansh? This is supposed to be 3D, it's just really hard to draw it. Okay. So you have four faces. Like what you have, like if I draw it, is that you've got a pyramid sort of like this. Right? But tipped on its side. Is that making sense to everyone? Or can we sort of see that? Is my drawing at least decent enough that you can imagine that I took this pyramid with the four triangle faces and I put this point right here, and then this base on the bottom is that thing right there. Okay, cool. Okay, so this gets a little weird to deal with. So you might start wondering like, okay, so it's a pyramid. Yeah, it's a pyramid stabbing the sheet of paper, basically, yes. That's like a good way to describe it. Okay, so you start wondering like, okay, like yes, this has volume. How the hell am I going to find the volume of this using a definite integral, which is supposed to be used to calculate area? And what you realize is that, let's go back to our definition of the definite integral. The definite integral was written like so, the integral a to b of f of x dx. And what was that defined to be? The limit as n goes to infinity of the sum of I equals 1 to n of f of xi times delta x, right? So where did the fact that this was an area come from? Well, it came from the fact that this f of xi times delta x, that was the area of those rectangles, right? This is an area because this was a height times a width. So f of xi times delta x was an area. And then what does it mean to use the sigma? The sigma notation just means that you're adding up a bunch of areas, so that becomes the estimated area. Right? Does it make sense? If f of xi times delta x is an area, sigma of that just means I'm adding up some areas. That's my estimated area. And then what do you finally do? Well, when you take the limit where the number of rectangles goes to infinity, really what that means is now that you have the actual area. So, because my function inside of the sigma is an area, that's why the definite integral gives you area. Not because that's the only thing it can do, but because I started off by calculating an area of a rectangle. You can do other shit is the whole point. Instead of starting with an area for your rectangle, you can start off with the volume of something else. And then I would add up a bunch of volumes. I would take the limit of that, and then I would get actual volume. So the whole point is that you're not... Does that sort of make sense? Like, you're not stuck with only being able to deal with area. If instead I did volume here, you would then get estimated volume, and then you would get actual volume. Okay, which is basically what we're going to do, and I'm going to show you how to do this. Okay, so let me show you how to do this. There's a lot of steps involved, so we need to identify those steps. Okay, so 1, do you remember how we had the formula for the xi? That was the partition from A to B. We're still going to have to partition. You're still going to have your delta x, which is the distance between all those points in your partition. Okay, so after you partition, your second step is going to come up with some formula that estimates something. So previously, we used the partition to come up with a bunch of different little rectangles, and each of the rectangles had an area. Now we're going to use that partition to estimate a volume, and we'll have to figure out what shape we're going to use, and then that will be our estimate formula for the volume. And then what will we do? After we have our estimate formula, we will sum the estimates, right? That's the sigma of AI. And then finally, what will we do? We'll take the limit of the sum, and then that will give us the actual whatever it is that we're interested in. So we're going to do a run through of like how this actually is going to go down. So let's start off with a shape. Here's our y-axis. Here's our x-axis. And let's say our shape looks like this. Oops. Okay. Let's make it go more like this. Okay, does everyone see my trapezoid? Okay, we're going to have a trapezoidal pyramid. And it's going to shrink down over to here to a smaller trapezoid. So this point is going to get connected to that point. This point is going to get connected to that point. Okay, this is much better when I actually use the insert line. Okay, this point will get connected to this point. This point will get connected to that point. Boom. So hopefully you can sort of see that this is a volume, right? It's designed so that any of the cross sections is like this, shoot, what's the right word? Trapezoid. There we go. I was like struggling for a moment there. Okay, so just like before, we start at x equals a, which is right here, and we end at x equals b, right? Okay, so what's the size of our estimate going to be? We're going to estimate the volume with a partition of size n. So remember how before we had to choose like n was the number of rectangles? Now we're going to choose n as some number of three-dimensional shapes. We haven't quite decided what that three-dimensional shape is going to be. Okay, so just like before, this is going to be our x naught. Oops, let's do that in red. This is going to be our x naught, our first point, and this is going to be our xn, the last point. And just like before, we're just going to have a bunch of points. And how far apart are each of those points on the x-axis going to be? So how far? Yeah, exactly, delta x, right? So once again, delta x is just b minus a over n, and each of those points is delta x from each other, right? So which means our xi, thankfully, is literally just still A plus delta xi. Yes. Okay, so all that remains the same. You're like, okay, cool. I can deal with this. Like, I understand this. What's different now is the shape that you're dealing with. So previously, we had rectangles, right? The rectangle was with delta x and height f of xi, agreed? And that's how we got our area f of xi times delta x, correct? Okay, it's going to be pretty similar now, but not quite. So what we're going to assume is, let's just choose some xi right here. Does that make sense that this point right here, that's xi? Let's put it this green point right here. I'm going to call that point xi. Now at the point xi, you can draw a cross section, and what's the shape of that cross section going to be? Hopefully you can. Yeah, exactly. So so this is called a cross section. And the interesting thing is that if you wanted to, you could actually figure out exactly the dimensions of that cross section if you had like all the information about this shape, right? Like, I understand it would be a little hard, but does it make sense that, does everyone imagine that you could figure out like that cross section right there has whatever dimensions and whatever dimensions? And you know a formula for its area, right? Because it's just a trapezoid. So if you tried hard enough, you could come up with an area formula so that you could find the area of the cross section at point I. At point xi. Now, that's like a rectangle, yes? Like the rectangle and the cross section both have an area, do we agree? Now, what happens if you take your rectangle and you fatten it up by a bit? It's no longer just an area. What is it now? It has volume. And when you fatten it like that, we call it extending it. Let's just say extension, right? If you extend out the rectangle in a new axis, you get volume. We're going to do the same damn thing with the cross section. We're just going to extend it out. And then now you get this like trapezoidal prism. There we go. Yes, a trapezoidal prism. So let's say, how do you do this? You extend it out some amount, delta x. The area of the cross section times the amount that you extend it out by will be the volume of the trapezoidal prism. So does it make sense right now? We have the volume of that one particular trapezoidal prism right there, right? We started with the cross section, and then we extended it out just a little bit, right? We fattened it up. Let me sort of draw you the shape that we have. Here's our trapezoid, and then we extended it out, and we ended up with this. Does everyone see how that's like similar to what I did with the rectangle, right? If you take the rectangle and fatten it, you get volume. If you take the trapezoid and fatten it, you get a trapezoidal prism, and that's a volume. So notice the area of the cross section times delta x is a volume. So you have then a brilliant idea. What if I do this multiple times? I then find my fattened prism over here. And then I find my fattened prism over here. And then I find my fattened prism over here. Does it make sense? You can break that shape up into like several different fattened trapezoidal prisms. How do you do that? Well, that's just doing the sum where n I equals 1 to n of AXI delta x. This is equal to the sum of the estimated volumes. And you're like, oh shit, that's going to be pretty close to the actual volume that I want, right? If you estimate that volume by like just a couple trapezoidal prisms, you're going to get pretty close to the volume that you wanted. Just like how we used to take the rectangles and add them together, and that pretty close to the area that we wanted. So if that's the sum of the estimated volumes, how do you find the actual volume? Take the limit, right? So you'll do the limit as n goes to infinity of sigma I equals 1 to n of AXI delta x. And that is a definite integral where we're going to be integrating from a to b. But notice now, instead of integrating f of x, what are we integrating? Big A of x, the cross section. So if you integrate these cross-section area formulas, you get the volume. Yeah, this gives us the actual volume. It's the same concept of how we got actual area, right? So this time though, instead of starting off with an area formula, we started off with a volume formula right here, right? We said, oh, let's just imagine that we have this cross section. If you multiply it by delta x, you get some volume right there. And then you're like, oh shoot, well, what if we just add up all of those estimates? And then what happens if we take the limit of all of those estimates? You end up with the actual volume, which is what you want. Okay, remember how in the previous lectures I talked about, oh, people just want to jump ahead to the integral at the end? This is why you need to know those steps, because you started off with this formula, which was a volume formula. But how did you get it? Well, it was some function times delta x, right? And then you're like, okay, well, what if I add up all of those? Well, that's the sigma of the area for function times delta x. And then you're like, okay, what if I take the limit of that? And then you're like, oh, well, that tells me what I'm integrating over here. Notice there's a similarity. Do you see how there's an a of x and a delta x? And there's an ax and a dx. That's like on purpose. Like, you should notice that. You always have to have that delta x there somewhere. If you don't have this delta x, you can't like transform into the definite integral, which is like a very common mistake that people make. Okay, cool. Okay, this is a good place for us to take a break. Okay, so just to sort of recap what we talked about, if you had a formula for the cross section, this gives you a way to set up an integral to find the volume. But you need to have that formula for the cross section. It's sort of hard to do usually, I'll be honest. Like most shapes don't like. Obviously, if you're dealing with a trapezoid, like, okay, cool, you can look up that formula. If your cross-section's like a triangle, not that hard to do. If your cross-section is a rectangle, not that hard to do. There's plenty of shapes for which this is not going to work. That's what we're going to discuss next. So,